Okay. Yeah, so we started working on this after this event. That was in 2000, 2.5 years ago, 3.5 years ago, 2021. The Champlain South Condominium Tower in Surfside, it collapsed just out of nowhere. And yeah, for somebody like me studying disasters, had to study this also, or studying hazards, had to study this also. And yeah, the Surfside, so there was tragically 98 people got killed. Champlain Towers South, where is it located? At the beach. The reason for the collapse was that they didn't do any maintenance. The building was pretty rotten. But there are the questions. What we were hoping to answer is whether satellite radar interferometry can help to contribute monitoring these structures, and whether the local geology played a role, could have played a role for the collapse. Yeah, just quick reminder on how the INSA technique works. We have our satellite flying around every 12 days, or 2 satellites, 6 days. It sends it's an active imaging instrument. It sends the radar signal. Then it comes back to the satellite. If you have some ground deformation in between, just a tiny fraction, using interferometric methods, we can measure it. And yeah, so then we're getting taking now lots of those images. Yeah, so it's an old example from Hawaii. We're having a network of interferograms. So we're creating interferograms between those different images. The network, we are inverting this, and then we are getting the time history, or the displacement time series. The persistent scatterers, or the scatterers we use, for which we get measurements. There's a number of different scatterers. Some of them are persistent scatterers. They are located, for example, on houses or high-rises. Then so it's a point scatterer in most cases, acting as a corner reflector, just sending the signal directly from one location back to the satellites. Then we are having distributed scatterers, where the signal is the result of yeah, so here we have the persistent scatterer. Persistent scatterers, they provide the strongest signal. Then we're having the distributed scatterers. So within one distributed scatterers, the signal gets reflected from multiple locations, multiple objects within this pixel size. And for this satellite is 5 by 20 meters. And then we're having areas where INSA doesn't work, where we have vegetation, the ground changes, we don't get any measurements. And yeah, so we are doing our computations on the Texas Advanced Computing Center, TAC. Yeah, before that we used the RSMAES or the facilities, but when they started charging, we moved to TAC, and that worked out pretty good. We're using a couple of different softwares. One software for INSA processing, software which is called ICE2, developed by JPL, partly by my previous students. And then for time series processing, we're using also a number of different softwares. MinPy, developed by Yunjun Zhang while he was a student here. MaplePy, it's doing high resolution processing, developed by Sarah Mirzari when she was a student here. And now for this one, we are using software developed by Andreas Peter Sarway, who is a graduate student in Hanover. Just to remind you of the geology and the problems in Florida. Of course, but if you plot Florida topography with a shaded relief, you can it can look quite mountainous, but of course it is not. In particular, down here in our area, we know there's no mountains, and yeah, because of that, of course, sea level rise is or changes in sea level have significant impacts. Yeah, 20,000 years ago, Florida was much bigger during the last glacial maximum, and yeah, in 200 years, when sea level has risen by another six meters or so, then Florida is going to be much smaller. Yeah, so sea level rise is a problem, and when sea level rise is a problem, coastal subsidence can exacerbate the problem. We know from a number of studies which were published recently that there is along the east coast of the US, there is it's based on a number of different things. There's different locations where there is significant subsidence in a couple of millimeters. In Florida, though, most of the Florida coast, there is no subsidence. That's what we thought. This study, by the way, is having tons of problems. It's pretty amazing that they got it published, but for Florida, it is probably correct, but there's lots of artifacts in there. So where are we looking? Our study area is here, Surfside, or the collapse condor. We're looking at the whole area. The collapse condor is in Surfside. And how does the Florida geology look like? Well, in some areas, most areas, well, we have limestone, of course, here the Miami oolite. In other places, the limestone has wax, significant voids, and yeah, so that is this part of the what is it called, the coastal ridge. But Surfside, Miami Beach itself, they are on barrier islands. The barrier islands were constructed from transported sand, which was brought in from the north. Couple of years ago, Szymon Worowiński and Simone Fieschi, who was a visiting student here when Szymon was still here at UM, they did a study looking. It was different purpose. They looked at subsidence, and in the 90s they found most of the area is green. That means no displacement, except a few localized places where it is yellow. And it turns out, and that is really surprising, the Champlain Tower's south side, there was subsidence detected, about, not very much, about 2 millimeters per year, but a small localized area. And that, of course, raised lots of questions about the potential geological impacts on the collapse side. An example of interferogram for the entire South Florida area, and yeah, so the location where the collapse occurred is right here. Okay, so these are the results. We had about 230 satellite images, SAR images. Szymon in his study and Simone, they used 23. So we are getting much more accurate results. And yeah, so most of it is green, but we have a significant amount of blue dots. And these blue dots indicate subsidence. In particular, so it's from north to south, in particular here in the Sunny Isles area, then in the Bal Harbor and Surfside area, there is a blue hotspot. In Miami Beach itself, there's hardly anything. Couple of locations to what I come to, to what I come later. And yeah, let me show some of those results in more detail. Here we have, so this time series that is for the Regalia. It was relatively recently built in 2014, 10 years ago. It shows more or less linear subsidence. all these buildings show some sort of subsidence signal. Here, the Marinas Beach, it's more or less linear, nothing is going on. Then suddenly there's subsidence happening. This one shows more or less exponential decay of subsidence. So these are our signal. There's an old building here, the Bentley residence development site, that has been, suddenly it shows subsidence that has been torn down since then, and there's a new high-rise being built, the Bentley residences. So let me, and these of course are nice buildings. Yes, I don't live there, unfortunately. So let me show you one example, the Porsche Design Tower. You can park, you don't have to park your car in front of the building. There is an elevator, so you can go to with your Porsche all the way to the 53rd floor. And so you have beautiful views, obviously, from the higher floors. And it's you don't want to go to the community pool. You need to own pool in an apartment. And so it's not quite cheap. So this was sold, the penthouse, at $32.5 million. And we know how expensive property insurance is. So they are paying something like $350,000 a year, which is $1,000 a day, just for property insurance. But
so
you're getting
tax. So it's insurance or tax?
Tax, insurance, of course, in addition. Yeah. But you're having your 11-car garage, which is of course important in the 53rd floor. And there's some famous residents. Messi is not. He used to live there. He has, since his family arrived, he moved to somewhere else. So how do we get our measurements? They're persistent scatterers. So this is an example. Well, it's a Porsche design tower. There are these structures on the roof. The radar signal comes from the satellite. It hits against it, then it's scattered back. If there's not all of these, some of those structures which are optimally oriented to the satellite. Similar for balconies. If you have a balcony which is perpendicular or to the satellite, then or to the look direction of the satellite, then we may get some signals, or at boardwalks or something like this. So you're doing your morning jog at the in Miami Beach, and the satellite might be watching you. Okay, let me go over the other examples. So up there in central Sunny Isle Beach or in Sunny Isles Beach, no matter really where you look, we are going to get those subsidence signal. Some of the buildings are a little bit older, the Trump International Beach Resort, for example, and also for more recent one, for example, the Jade was built in 2018. We don't have data, or the Muse, we don't have data for the very recently built data because structures, because they're just being built. There was no persistent scatterers during the time period we observe. We also don't get measurements during the period when the buildings are constructed because the surface changes. A little bit further south, same thing. And Bal Harbor and Surfside, there is one place where we get quite interesting signals here in the surf club hotel area. Champlain Tower South is just north of the 87 Park Tower. If you go further south to Miami Beach, so there's essentially nothing, but there was also no recently built buildings. The few ones which were recently built is the L'Atelier and the Finer Forum, Finer House. Next to it is the Finer Forum, and the Finer Forum, we have no data. It is that's a cultural center or a concert hall or something like that. the way it was built, there is no scatterers. In total, so lots of subsidence. In Sunny Isles Beach, we have as much as 70% of the structures subsiding. A little bit further south, in the next town, next municipality in Bal Harbour, there's hardly anything, 3%. In Surfside, again, quite a lot. And in Miami Beach, hardly anything. Yeah, and so let me explain you some of the difficulties or of doing these measurements. When the satellite observes, we are taking the satellite comes from here. The first signal what we get is, in this case, from the top of the high rise. So there we have to be very careful with locating those pixels. When you publish this, we want to be sure that it's really that we attribute the pixel to the right building. So here, for example, yeah, this is for the Oceania residences. Originally, the pixels show up here to the side of the building, about 80 meters or so to the side, and that just makes lots of sense. That is, yeah, because the building is something like 80, 90 meters high, so that's where we get our first scatterer. And then we can estimate the elevation from those scatterers, and so we are ending up with estimated elevation of something like 80 meters. Here is a digital surface model that is more or less the same altitude. So that makes lots of sense. That so we can be pretty sure that these pixels are located on the roof. Okay. Yeah. So this foreshortening effect, if you want to do urban INSAR, it's quite tricky. This is now a different satellite, just to illustrate it from the Terrasa X. It's looking from this side, and all these buildings, they show up in the ocean, or the top of the roofs of the buildings show up in the ocean, because that is from where the signal is returned first. So what we are doing then, if we have the estimated elevation, we can correct the location of the pixels, and then they show up on the or that's the velocity, they show up on the building. So that's good, but there's quite some difference. So some of them are showing 0.6 centimeters per year of displacement, and others don't show anything. And that was really surprising to try to understand this. And yes, so you can't do any mistakes as people are living there. So but if you look at the building. If you look at the building itself, in this case, there's an opening. We estimate, so the elevation, what we have, we also correct it, and then you're ending up with some pixels over here which are at 80 meters, and other pixels which are at 0 or 20 meters. And what we think, what is happening is, yeah, those pixels, they are from here on the ground area, whereas others are on top of the roof. And if you look at the velocity, at the subsidence, that makes sort of sense. The yellow ones, they don't show any subsidence, so they are somewhere not on the building. They are next to the building from some reflections in there, and yeah. So so that we are struggling with this for a long time, trying to be sure about these results, and so I think at the end it makes lots of sense. Yes, we want to be sure that our results are correct. So what we did, we got some colleagues involved. This is our result. They calculated it with a different software, and then we also have a different satellite. It roughly agrees. It doesn't agree 100%, but that is because we process different time series, different time periods, and in this case, the scatterers are not the same because it's a different satellite. So anyway, we could be quite confident that this is correct. An interesting spot where we had a significant signal is the Surf Club. That is one of the first hotels what was built on the Barrier Island in 1935 in Surfside. Since then, of course, so the question, one question was, and this is a place where we see significant subsidence, is could there be any geologic reason that they built the surf club right there, and could that be the reason for the significant subsidence signal? This is how the surf club looks now. It's a historic building, so they were not able. They didn't get permission to tear it down. It is still it's still standing there, but they built the new structures 12 stories on top of it. And this is the signal for this structure. It's a little bit surprising. First, it is nothing happening, then significant subsidence, 2 centimeters, and then slowly decaying. And so what could be the reason? It turns out here there's a hole. In the meantime, there has been a structure built, the Arte residence, and this subsidence signal roughly agrees with the time period of the construction of the Arte. So I think that is the reason. So we have 2 effects. The surf club itself, the new structures were completed in 2016. The longer term signal is probably the result of this. The subsidence is a result of the construction of the structure itself. And then we have this signal from the Arte overlay. So what is the reason for our subsidence, for the observed subsidence? So we did see, we got some geotechnical exploration reports. These are geotechnical investigation which have to be done before they build one of those high rises to know what kind of foundation they built. And we didn't get much, but so the upper layer is sand. And this sand is actually from the barrier island that was deposited in the last 4,000 or 5,000 years. After that, we have quite some limestone, and there is some sandy layers in between. The SBT test, that is something what the geotechnical engineers are doing. So essentially what they're doing is they are hammering on something and measuring how difficult it is to get a rod into the ground. It shows some areas where the limestone or whatever it is pretty hard, whereas other areas is much softer. So here, for example, for the 87 Park Tower, it's pretty soft, and there it gets harder. So in general, what we can see from the little amount of data what we have is that further south in these places, 87 Park and L'Atelier, there is less sandy layer than in the north. And in the 87 Park, it's pretty weak, as shown by the SBT test. There's a couple of places where we have information on the geology from USGS drill holes, and it's further south in Miami Beach, Stillwater Park. That's quite surprising. There's actually at 16 meters there is a void, significant void. Half a meter of material or so is missing. At greater depth, it looks like what we expect for the limestone. Other places. Fisher Park, there is significant sand in the limestone. And most of it is limestone, but we do have those sandy layers. And if we look at this is a satellite, this is a core from somewhere else, a little bit further south in Miami Beach. Some of the samples, they look like limestone as you would expect, a little bit wuggy. There's quite a lot of material missing, and the fact that it's missing, it's because it was sand and it was difficult to retrieve. The way how for construction this geotechnical coring is done, they don't care about the sand layers. Okay, so what could cause the subsidence? When it comes to subsidence around the world, the typical explanation is groundwater extraction, but in Miami Beach there's no groundwater extraction. Another possible explanation is consolidation. That is when you build a high-rise, for example, in Chicago, in the alluvial around the lake, you're putting the big high-rise on top of relatively soft material, which contains water. This water is then being pressed out, and for that, you're getting slow subsidence. In the limestone of Miami Beach, that can't really happen. Another possible explanation is natural compaction under the weight of the structures. That happens if you have somewhat similar to the consolidation. It happens if you have weak materials, but in places like Miami Beach, or the barrier island, the geology of Miami, it's very, very unlikely. So the most likely reason is that the subsidence is construction related. And so our hypothesis of what is happening is this. You're building a high-rise on the limestone. Here we have the barrier island layer, then we have sand at depth. The construction is associated with significant vibration, seismic signals. The limestone originally, or the sandy layers, not the limestone, the sandy layers looks like this. Then we have the shearing by the seismic waves. It goes first in this direction. It goes then in the other direction. And if you do that for a while, then it results. We're getting a repacking of the. We're getting a repacking or rearrangement of the granular medium, and so the result is subsidence at the surface. But so they don't really vibrate anymore, because it's nuisance to the neighbors. So they're trying to mitigate or to really minimize vibrations for the construction. Another possible cause, and so these are speculations. Even if they don't vibrate for the construction, there's lots of pumping going on. And if you pump, then water continues to flow to where you pump to equilibrate the pressure. So there's significant water flow through the sandy layers, and that also could lead to grain rearrangement. Let's look a little bit at the spatial pattern from. This is now not from the persistent scatterers. This is from the distributed scatterers. One place here, 87 Park, that turns out to be right next to the collapsed condo. We see a subsidence signal just of the building itself. Nearby is there's some noisy pixel. The distributed scatterers are not so. The measurements are not so accurate. But anyway, it's only the structure itself which is subsiding. If we go, if you look somewhere else, this is in sunny Isles Beach. Here we have, for example, some lighter green or dark green pixels right next to the building itself, to the substance from the building itself. So it looks like that, there is some areas where the subsidence doesn't only occur for the building, itself. But so the spatial patterns are a little bit difficult to interpret. Easier to interpret are the temporal pattern. So we observe a couple of different patterns. Exponential decay, for example, for the Ritz-Carlton residence. And the easiest explanation for something like this is really, it's the after effect from its own construction. So that is quite a couple of years ago. And when these buildings are constructed, so what we see is only once the building is done. That's why the time series here starts in 2019. During the construction, there is significant subsidence settlement going on. Some of those high rises, they might settle by as much as 30 centimeter. But so the high rise in its entirety settles. That is not really too much a problem. Then we have, as I showed before, we have some places where there was subsidence going on, slow subsidence, and then we have some acceleration. This is for the Trump Tower 3, and next to it, so these pixels belong, if it's geo-corrected, they belong on the structure. Next to it, the Ritz-Carlton was constructed. So possible interpretation here is that, this acceleration is because of the construction of the Ritz-Carlton. But then we have also some buildings which show a linear subsidence. The Oceana, maybe not quite. Here it's exponential decay, but then it just seems to continue linearly. And the regalia, it's not moving very much, total of 2 centimeters, but it seems to be more linear. So what could be the explanation for the linear subsidence? No decay, which we would expect for construction related. So this is complete hypothesis. Possible mechanism is tidal flow. So under the buildings at the coast, we are getting the twice a day the tides. And if the tides go through the sand layers, if you put a heavy building on top of it, then maybe you're going to get the rearrangements of the grains as a result of that. And another possible explanation is the dissolution of limestone from stormwater injection. So what they do in if you look in Miami Beach, so we're having the barrier island, we're having the bay here. There's a salty the salt water. So the limestone and sands, mostly limestone, is all saturated with salt water, which is what how limestone are deposited from salt water when they grow. Right under the barrier islands, there is a freshwater lens, and now it's raining a lot. It's raining more and more in Miami Beach, and so to get rid of the to get rid of the storm water, lots of these structures are having injection wells. It's something what was pointed out by Mike Zucker when he visited. And so you're putting fresh water into limestone. And even with my limited geochemical expertise, I know this is not good. So that is something what can dissolve the limestone. Limestone dissolution is something which is supposed to be very slow at rates that hardly detectable, but it's imaginable that if you're putting a heavy building on top of it, and then you have underneath the limestone dissolution, that this contributes to the subsidence rates what we see. And these injection wells, there's plenty of them. Each high-rise has a couple of them. They are injecting into a depth of something like 120 or 150 feet, 30 to 50 meters. Okay, to summarize the signals of those structures, what we see, so this shows the average velocity for all those structures. In Sunny Isles Beach, they are pretty high. Down here in Surfside, it's only allowed to build 12 stories, so that's why the structures are not so high. So we see essentially subsidence from a total of 35 structures. How does it compare with the age of the structure? So here they are now sorted by age. The oldest one are at the top, the youngest one are at the bottom, and all these structures are built before 2020. So this is quite a long time ago. They are 15 years old and they are still subsiding they are not so high, at similar rates almost as the younger ones. And that is of course a little bit that was really a surprise to see that. Oops, that was not meant to be there. Okay. Another question was, what is about the collapsed condo? We have a few pixels right on top of the condo, on top of the roof, and it doesn't show much of a signal. Essentially, it doesn't show any signal. So there was no subsidence going on in the years before. We thought we might be able to see some precursory deformation just a couple of days or weeks before, but we don't see it either. There were some precursory cracks observed on the pool deck, and yeah, this is an area. Well, if there's cracks, if there's ground motions, we should be able to see it as long as we have some persistent scatterers. But the radar is looking from that side, so in this side, in the pool deck area, we don't have any persistent scatterers, any measurement points. Another surprising result is there was heavy vibrations going on for the construction of the 87 Park structure right next to the collapsed structure. We have significant subsidence, as I showed before, of this couple of 0.35 centimeters. So there was the vibrations. So we would expect that the vibrations from this one would create some subsidence over there, but we don't see it either. So that is, it is really surprising. It made it difficult to understand, but that is what the observations show. And yeah, something what is of concern is differential settlement. Do we have differential settlement? So if you have a building going down as the entire building, just like one, it doesn't really even settlement, it doesn't really matter very much. Differential settlement is that what can cause problems. We don't have much differential settlement, but we have a little bit. Here, for example, in the Surf Club Hotel, there are 2 pixels with different velocity, 0.3 different, and they are right next to each other with the same elevation. In the 87 Park, the same thing. So there is some differential settlement, but most of the signals, what we see here, it's all going down with more or less the same velocity. What about tilt? Yeah, so after we did most of the study, we looked a little bit more with the other satellite, and actually the maximum displacement we see it at the Porsche Design Tower. This year is now colored according to the elevation, not according to the speed, and we see up to 12 centimeters. So that's quite getting more significant. And that is from one satellite, Terrasa X, looking from this side. Then we have Sentinel looking from the other side. Most of our observations, what I discussed here, are Sentinel, and we see 5 centimeters of loss displacement. So we have a 6 centimeter difference. That is a little bit surprising, and the tilt of the whole structure towards the west could be the reason, and that agrees actually with the persistent wind direction. The wind always mostly comes from the coast, comes from the water. So maybe the wind is slowly tilting those buildings over, but it's not very much. It's 5 centimeters. You would think that this was taken account in the design, but yeah, maybe not 100%. So other places where we see subsidence, actually quite a lot, and we haven't looked at it in detail. In downtown Miami, there is significant subsidence. There it is a little bit more, or it's quite complicated to assign the pixel to certain buildings. We don't really know where the scatterers are. Something to do in detail. And there's a couple of buildings over here. One of them is the Panorama, where we do see subsidence as well. Regarding the mechanism, so we are dealing with granular material. Granular material can exhibit some strange behavior. So it's a study done 10 years ago by material scientists. It is vibrating a little bit at distance, and the granular material react in this case, well, we see what's going to happen. But I'm not saying that the condos of Miami, that the same thing is going to happen to the condos in Miami. So is there a concern? In summer, I was in China, in Decheng, in Zhejiang province. I stayed, there's lots of high-rise, lots of construction. I stayed in a high-rise. And the first thing what I did was to process the data, and there's actually lots of blue dots. I stayed somewhere here with this good blue dots. There was something like 20 centimeters or 10 centimeters of subsidence going on, but the building was safe. You could even see one of the students. The students were also living there, and there were some cracks observed. But in this case, so they are still standing, and I wasn't really concerned. So these high rises are really built very well. Example here of the Mercedes-Benz residences a couple of months ago, a very strong foundation, couple of centimeters. Well, the subsidence doesn't really matter, and even a little bit of differential subsidence, I don't think it is a big problem. Amazing large amount of concrete, amazing concrete pours. What is done there? Couple of actually last week I was in Sri Lanka, and of course the first thing what I'm doing is processing the INSAR data. There's the high rise of Colombo. This is what the INSAR data show. No subsidence at all of those high rises. And the explanation for that is Sri Lanka, well, the high rises there, they are socketed a couple of meters in crystalline metamorphic bedrock. So it's a different, it's a different bedrock. It's not limestone like we have in Miami. Regarding the tilt, if we have a couple of centimeters of the Porsche Design Tower in San Francisco, it was also detected originally with INSAR. There's a leaning tower of San Francisco. We have there was a total of 70 centimeters tilt at the upper. So it was really a problem. If you put a marble on the ground, then it went in one direction. There still is some expensive. Well, they're repairing it, trying to fix it, but it doesn't really affect the integrity of the structure. And of course, we have a couple of leaning towers which are still standing since quite a long time, like the leaning tower of Pisa. There's that's interesting, a couple of other places where we saw signals after the Surfside collapse. The Broward County Courthouse was closed because of possible cracks. We do see subsidence. Is it related? One area where Emian looked at, that is a very strange signal. That is in Broward, the Hugh Taylor Birch State Park. There is nothing going on up to 2021, and then suddenly we see subsidence. There was some seawall repair. Maybe that's some very weird geology. We don't know yet what's going on. And there was no construction, no evidence for construction at all. So if the same mechanism applies, then maybe it's related to the seawall repairs. And I suspect some locally very weird geology. Okay, to summarize, we see in most buildings between 2 and 8 centimeters of subsidence. Interestingly, 20 of those structures were built prior to 2010. So you can a little bit imagine if this continued for a long time, how much that has been. It's caused by grain readjustment, mostly due to construction vibration, but pumping and tidal flow, stormwater injection can also play a role. Nothing was detected at the Champlain Tower South. And something what was in the news articles, what were written after this is, we had Barrier Island in the title. The fact that we are on a barrier island actually doesn't matter at all. It creates a sand, the uppermost 6 meters or so, but after that, the geology, the barrier islands, started to be to grow maybe 10,000 or 15,000, 10,000 years ago, 6,000 years ago, when sea level came close to the current level. The geology at depth, what controls the subsidence, is from a different time. So what next? Well, we have to look to understand the subsidence. So it's actually pretty obvious what we need to do. We haven't done it yet. We should look at edge water. If we don't see anything over there, only at the coastal, really at the coast, that gives some indications about the mechanism. And same here, close to RSMAES. Would be great to get more geotechnical exploration reports when they build those high-rises. We hardly got anything. Then if we can combine, if we can develop a database, geologic information, foundation type, building height, then that will help a lot to understand what's going on. We hope to do eventually to get the vibration information using a DAS, distributed acoustics sensing network. Wrote a proposal, didn't get funded. Maybe hopefully we will get eventually proposal funded to get some sediment core and do some geotechnical testing of those interbanded sand. That is what is really needed. We just have a hypothesis of what's causing the subsidence, and we need to get those. We need to get those samples. In the longer run, it would be great if we could do we have to do some studies whether this technique can be used for monitoring the building stability. We need to look more at differential subsidence, and there was a couple of condos which were evacuated because of construction difficult problems. Do we see any precursory any deformation on those? That's something what we hope to do. So this caused quite some caused quite some attention in the media. Until this is happening, so normally I'm doing tectonics. Tectonics is much faster than the subsidence over here. So 100-meter subsidence, it will take another 20,000 years. And so there is, again, thanks to Fasani, who did the heavy lifting for all this, literally. And I'm going to stop with this Terrasa X image of sunny isle speeds. Thank you very much.
Thank you. That was very interesting. So I think we have time for questions.
Thanks for the updated presentation. I'm trying to understand this granular rearrangements. So do we expect a linear or exponential subsidence from this arrangement?
Exponent. Well, I would expect. So I don't understand it. I would expect an exponential decay because you vibrate and then somehow whatever effect is, it should decay eventually.
Yeah, that's actually related to my next question. So if this rearrangement is a dominant mechanism, would we expect the displacement will be stabilized eventually? Is it everything will be just rearranged, right?
Yeah, so if it goes really exponential, then it should stabilize. But we have some indications that it's not stabilizing; it just continues
maybe it's not
linearly.
Yeah, it takes time.
Maybe it takes time. Yes,
Sorry.
but so if it depends on the mechanism. So if it is really related to the tidal flow or to stormwater injection, then there is no reason. Unless all the sand has been compacted already, but there's lots of sand, so there's not really a reason for it to stop anytime soon. But we don't know. Time will tell. Yes.
I have two questions that are probably not like very public, but when you were studying the reasons for subsidence here, and you were making like the list, then saying which ones, like the idea that like the subsidence in construction is probably the most important one here in like the barrier islands. The option before that was like just like the compaction due to the natural weight of the building. And you were saying like that probably that is not something that happens here.
Yes.
My question is why basically, because when you were showing the geotechnical data, so like the layering of like limestone and sand, and how strong those are, you were showing also that in some of these, I think most of the buildings, at least the very first part, it's pretty weak. Like the curve was showing that it's pretty weak, and you said that this is something that happens for base soil. So I guess you said that it's like this compaction is something that happens for weak soil. So I guess I'm confused about why that is ruled out.
Okay, so I didn't fully. Okay, I didn't fully understand the question.
Sorry. Yeah, if you look at it, like you're showing that that is pretty weak, like the like the strength of the soil. I guess the red curve is showing that it's pretty weak. So why is compaction not more important, like compared to construction?
So, yeah, weak soil means, I mean, it is still rock.
Okay.
It's not. It's still. Yeah, I don't have the image here. I think it is in the. Yeah, if you. Okay, that is a type of material what we have. Just putting material on top of it. Okay, when you build the high rise, right at the beginning, you get subsidence because it breaks, it compacts, and you get a lot. As I said, up to 30 centimeters for some of the really high rises. But so yeah, so if you do the SPT tests, in between there's probably sand, and here the SPT test would give relatively high values. But okay, so it's not going to break so easily because it breaks at the beginning when you put the load, but then slowly it's not going to not necessarily going to break. But that is not okay. So what was exactly your question? Sorry.
Basically, okay, so I think you answered. Basically, it's like something that you expect at the beginning, but then the fact that it's sustained in time, then that is not explainable by the just compaction due to weight.
Yeah.
Okay.
Yeah. Okay. And the geotechnical engineers, so they expect, I mean, that's what they write in their reports. You get subsidence a couple of weeks after it is, or settlement after the construction is completed, and that is the natural settlement because of the load of the structure on the breakable rock. But then it should stop. Yeah.
And so that's what makes you say that it's probably construction. Construction of other buildings.
Yeah. So no. So that makes us say that it's not related to this material.
Yeah.
It's related to the material, this is a good example, to the sandy layers.
Yeah.
They are going to be rearranged, we think, as long as there's a load on top of it. If there's no load on top of it, for example, you have tidal flow or construction vibrations. Yeah, if you have no load on top of it and just construction vibration, okay, it vibrates, it doesn't compact. Because there's not much load on top of it. But then if you put the load in addition and then vibrate, then they rearrange.
And do you know what the horizontal extent, like if I do construction here, how far horizontally do I get this effect?
Yeah, so we have some indications for sudden onset of subsidence at 300 meters from the construction site, which is far. But we don't know how. So if that sudden onset at this old building is caused by the construction, then that gives you the number, but it's the distance. But whether this is really caused by it, so it's hard to tell. Yeah. Yes, right.
I was wondering what your current hypothesis hypothesis for the Surfside Tower collapse, then do you think that it was differential subsidence, or do you think that it was purely a artifact of the structure? So,
Well, it was
Bad construction.
rusted. They didn't do any maintenance. So there was so that is actually there the differential subsidence comes in. There could be that there have been differential subsidence at the beginning, but so differential subsidence is a problem. You get cracks, and then you get the ocean winds, and then it goes into the cracks, and you get corrosion at places where you wouldn't expect. But in the Surfside collapse, well, they didn't have they knew they had to do repairs, but they didn't have money to do repairs because so that was in the news a lot. But if you don't live in a condo, then you don't necessarily follow that. The Florida law didn't require condominium associations to put money to the side. So they realized, okay, we have a big repair to do, but they didn't have the money. So they would have to assess the condominium owners to do the repairs, and they wanted to do the repairs, but the repairs were done. Did you get any assessments? You
My
got
HOA fee is double right now, compared to before this.
it's double, yes. So it's for insurance. Yeah, so that's what I think eventually, it's not very difficult to monitor this. It could help to reduce costs a little bit.
Have you thought about looking at to test this like vibration, liquefaction? Have you thought about looking in places where they have earthquakes and big buildings, and trying to see whether you have a signal after earthquakes? I guess it'd be a little bit different, but
Yeah, so it would be completely different geology, you mean? Well, here we don't have
yeah, I guess I'm just thinking of
much earthquake,
vibrations, but like Mexico City is that's alluvial sediment.
it's alluvial.
Yeah.
Yes, it's completely different. So
Is it so? There's no way.
yeah, so yeah, I think if you get an earthquake here, then this, according to our hypothesis, it shouldn't make a big difference whether it's vibrations from construction or whether it's vibrations from earthquakes. So if you get some earthquakes, which we got recently, but it was far away, it was not local, so no high frequency. I think the frequency content will matter a lot. If you have a slow wave from somewhere, from a fault somewhere near Cuba or so going here, then it's not going to affect. But if there would be a local earthquake, yes, probably.
we have one more question from Peter. Peter, you can unmute yourself.
Hey, Falk, that was a great talk. I had two comments, one question, two questions, I guess. First of all, did you ever have a look at the Rosenstiel buildings?
You mean right here in our campus?
Yeah. North Grosvenor has been up since '66, and it's about the same height. And not really that much different than that other one you showed, which had a presentation.
But we haven't looked. There's lots of places. Yeah, we haven't looked. We should do, but we haven't done it yet.
Well,
What I did,
the reason I asked, I think I said this before, but when they built the slab, some of us were here when that was built. They used this vibration method, and so they pounded the hell out of this place for months. So obviously you can't, the satellite didn't go back that far, but it could be, worth looking at. And basically
30, 40
bring it
years.
home to the university, I think.
Yeah. So it's a 30, 40 years after construction. Yeah, maybe. But so do we have sand right here, or do we have more limestone? Just my limestone. We don't know.
I don't know. I think there's sand because we're basically at the tail end of longshore drift. The Key Biscayne is mainly longshore drift sand. So I think, it's worth looking at. I had a second point, and I think I've mentioned this to Gregor, but I think, you should be aware of that. when you have the interface between freshwater and saltwater, there is a geochemical mechanism which causes the water to become even more corrosive than just fresh water by itself. So it's called the mixing zone, and the reason is that there's a phenomena which is related to the non-linear behavior of the activity coefficients of ions like calcium and carbonate, which causes the resultant mixture to become very unsaturated and corrosive, even though the two end members are actually at saturation. So that would happen, certainly below the coastal ridge, and also probably below Miami Beach, where there is an ephemeral freshwater lens, and perhaps related to the discharge of all that wastewater or stormwater that they're pumping down.
Okay, yes, very, very, very interesting. This limestone dissolution thing, how much do you think subsidence, or how much could it dissolve? What Gregor said was something like, yeah, well, 1 millimeter per year would be a lot, but given that there's a heavy building on top, it's maybe possible. What would be your take?
Its volume, it's not sort of it doesn't reduce the height initially. It basically causes cavernous porosity, and certainly you can calculate the amount of calcium carbonate which is resulting from the dissolution just by rainwater, and then along the coastal zone there'll be even more, and we can see this particularly down in South Miami-Dade, not where you're looking, but if you go further down towards Turkey Point, which is really the lowest point in Miami-Dade County, where there's a lot of saltwater intrusion, you can pick up this process in the geochemistry of the water, even the canal water, because it really changes the certain ions in the system. So I don't know if there's been any serious look at water wells up in Miami Beach or up further north at all, but we certainly know that's a lot. And obviously, since the last 200 years, the amount that has increased by is quite a lot. So just on a statewide basis, of course, it's sort of a ridiculous number because there's a lot involved, but so it's thousands and thousands of extra tons of calcium carbonate are being dissolved each year just as a result of increases in the PCO2. I use that as an example in my geochemistry. Oh, I used to, when I taught geochemistry, I used it as an example of, just to see how much, this phenomena due to global, increases in carbon dioxide. But anyway, it's a lot. There's a lot, but it doesn't actually. But because it's a system, it's a framework system which is supported by cementation and so on. So just by dissolving it doesn't actually really make the structure initially unstable. Eventually, of course, these things collapse. They cause sinkholes, and if you go to places like the Bahamas, there are these blue holes, and they're all caused by this phenomena of dissolution underground. Eventually, the roof collapses, and you get a hole. And we don't have that too much in South Florida, but a little bit here and there.
Yeah. Well, anyway, it would be good to do an experiment to see how, what kind of rates we get. Maybe, okay, we should talk about that at some time. Yeah.
Yeah. So geochemistry does have an importance.
Yeah. Could be all right. Okay. Any other questions?
I think we are set. Thank you for being here. See you in 2 weeks. It's 2 weeks. 2 weeks.
Okay.
Subsidence.